Hello, everyone, and welcome. Good morning, good afternoon, good evening, as the case may be. Here it's evening. And thanks for joining us today. Welcome to this Ophir Photonics webinar. My name is Mark Slutsky, a Senior Product Marketing Specialist for Power and Energy Measurement Solutions here at Ophir Photonics. And again, thanks for joining us. The topic that we're going to be covering is one that we probably don't cover enough, and that's basics. I think, as is the case in any specialized professional area, people who are involved in their specialty niche might not always realize that those they work with might not necessarily be as involved in that niche. And many of you are very likely, very experienced professionals in some kind of a laser system application. But every now and then, when the question of monitoring and measuring comes up, you don't necessarily know what gibberish we're talking about. So every now and then we have to remind ourselves, okay, not everybody does exactly what we do. They do what they do. And we felt it would be a good idea to have a discussion about really the basics. Where do I start? As we wrote in the invitation, okay, I have a new laser system, laser, whatever. I know enough about these sort of things to know that I need to keep track of what the system is doing, how the laser is behaving, so that my process, my research, my whatever it is, will do what I intend it to do. So I know that I need to measure my laser's what. So that is what we're that what is what we're going to be talking about today. Let's move along. I'm assuming that those of you joining a webinar like this are at least somewhat familiar with Ophir. I mean, we've been doing this for over 4 decades. You might be already a user of Ophir solutions or somebody else's solutions, God forbid, or you might just be in the process of learning the issues. Either way, I hope that this will be helpful. Some years back, Ophir was acquired by Newport, and then some years later, Newport became part of MKS. Basically, what it said on that slide is that we like to do the hard stuff that you would be very happy to get off your head so that you can focus on your work and not have to lose any sleep worrying about the tools that you'll need to help you get your work done. I think that's a reasonably fair summary of what it said on that slide. I've done what I could to keep the information as generic as possible so that it would be as helpful as possible to as many of you as possible. With that, when I show you actual examples of real instruments, you can appreciate that those will be Ophir instruments because obviously those are the ones that I'm able to talk about. So here's basically what we're going to be covering. Just for maximum clarification, I'm going to spend a few seconds, a few minutes, just giving a brief overview of what lasers do. We're not getting into the physics of how they work, much as I would love to, but I will resist the temptation. But an overview of what they do for us, and what makes them lasers. That'll make it easier to then move on into the rest of our conversation. So we're going to talk about which laser parameters make a given process happen, and more importantly, how do you decide and how do you know? Because those are the ones that you're going to want to measure in your particular situation. And then we'll talk about when, why, and how we need to monitor those. And we're going to explain what the basic parameters each mean. You'd be surprised at how often just that preempts and prevents a lot of potential problems. So let's begin with what our lasers do, what they are, what they do. So we have what we call classical light sources. Think of an incandescent light bulb. Some of you hopefully might still remember what those are. And basically, a classical light source is giving off photons of light, but each photon is completely uninterested in each other photon. Different wavelengths, different phases. There's no phase relationship between them, each going in a different direction. Think of a crowded room full of people, each of whom is moving around at different speeds, different directions, minding their own business, not even looking at each other or talking at each other. They probably have their faces in their mobile phones. So that's a good way to think of a classical light source. In a laser, on the other hand, all of the photons are related to each other. They all have the same wavelength. I'm oversimplifying things a little bit drastically, but I hope that's okay. They all have the same wavelength, at least in principle. They all have the same phase, meaning they're marching in tune with each other. That's why I've got this graphic over here. And they're all usually moving in the same direction. Those little S's at the bottom are meant to be waves, and I was trying to illustrate the idea of all the photons are in the same phase as each other. Um, with my limited artistic abilities. And what this basically means, bottom line, and skipping over a whole lot of physics, is that a laser beam can bring a lot of power concentrated into a very well-defined small area, even over long distances. Now, that very small spot, true, even a regular classical light source can be focused down to a small spot, as any kid who ever played with a magnifying glass in sunlight knows. But when all the photons are in phase, or as we say, the beam is coherent, it can be focused down much, much more. Um, Now, as opposed to the magnifying glass in sunlight, let's think of more modern examples. So you see some examples of modern, let's say, industrial material processing applications, medical applications, laser-based surgery or imaging or whatever, telecom research. In other words, we can use the power that's being delivered in a laser beam. We're going to explain what power means in a second, to change matter, by which I mean modifying the matter, cutting, burning, zapping, vaporizing. For example, burning it selectively to cut or drill, as you see in the image on the left, or in the middle for that matter. We could cut or drill industrial components. We could cut or drill tissue in a surgical application, or melting it selectively for additive manufacturing applications, or selectively exposing photoresist to create patterns on silicon wafers and produce microchips. Or we can use the beam to send light, for example, communicating by sending light signals over a fiber to a receiver far away, or sending light signals to the moon or to a military target and measuring the time of flight, as we call it, the time it takes for that light to go to the target and back, and by measuring that time, knowing the distance. Or sending 30,000 light signals to a whole bunch of spots on a human face and measuring the time it takes for each of them to return, and thereby create a 3D map of that person's face for facial recognition purposes. My cell phone is a little bit lower down on the scale. Facial recognition there is done with a camera that's not very secure because that can be fooled by a photograph. And higher end instruments, they actually use a little LiDAR chip built in. You can kind of appreciate why it might be of some interest to keep track of the power in those beams. Okay, so that was our overview. Now let's talk about laser parameters. Which ones, how do I know which parameters are of the laser beam are the ones that make my process or experiment happen? So first let's define them, because as I said, you'd be surprised at how often just that can prevent a whole lot of complications down the line. So the basic laser beam parameters that we're going to talk about and we're going to explain what each of these means in a moment. There's energy, power, also energy density, energy per unit area incident on a surface, even if there's additional energy going to other places. Also power density. There's also the beam profile, by which I mean the spatial distribution map of the power in the beam's cross-section. We're going to touch on that briefly shortly. Also the temporal profile, the shape of a laser pulse in the time domain, the duration and how it's behaving during the course of that pulse, even if the pulse is a few nanoseconds long or 100 milliseconds long. That can be important in some applications, such as LiDAR-based distance measurement, which we mentioned a moment ago, since with LiDAR, we're basically measuring the time of flight of the pulse in order to determine the distance. So the time, shape, and width or duration of that pulse obviously is going to affect the distance resolution with which I can measure. Because if it's a very long duration pulse, it's going to be returning to me over the course of that duration, which means my calculated distance is going to have a certain, an uncertainty built in. So now let's explain what each of those parameters means. So let's begin with energy. I think it's the most basic one in physical terms. Energy, we can sort of define that as the quantitative capacity for doing work in the physics sense, not in the human sense. So for example, 1 joule, which is the basic unit of energy in the SI system of units. A joule is the energy that you need to raise the temperature of about 1/4 of a gram of water by 1 degree Celsius. So it's a quantity of capacity to do work. You can think of an image of a container containing a certain quantity of fluid. Having grown up in Canada, I take a certain pleasure in forcing Microsoft PowerPoint to accept my Canadian spelling of the word leader. The things that give us a feeling of worthiness. We live in funny times. In some applications, I might have a repetitively pulsed beam. So think of a sequence of pulses. Each of them might have energy that's different from the energy of other pulses. In some applications, I might want to know the energy of each of those pulses individually. And in other applications, I might not really care. I just might only care about the overall rate of flow of energy. Depends on the nature of what I'm doing. So if we just run with that same imagery, we have that sequence of containers of fluid. Power is the rate of flow of energy. 1 watt of power is 1 joule per second. I can talk about the power in a repetitively pulsed beam. How many joules per second do I have whizzing by? I can also, of course, talk about the power of a continuous beam, a CW beam. With a continuous beam, of course, we can only talk about power and not about energy because there is no fixed quantity. There's only flow. Couldn't find the clip art I needed, so I kind of had to make up my own. Now, just a little clarification because this comes up every now and then, and we get asked for an explanation every now and then. Let's think of a repetitively pulsed beam where let's say each pulse has 1 joule of energy and they're coming in at 1 hertz, 1 pulse per second. So the power, and I'm going to call it the average power of my beam, is the rate of flow of energy, 1 joule per second, 1 watt. That's the average power of my beam. But in some cases, I might want to talk about the instantaneous power during the course of one pulse. Now, let's say that pulse is a millisecond long. So the power during the pulse, the instantaneous power, or peak power as it's often called, is 1 joule per millisecond. So that's a kilowatt of power. So my average power is 1 watt. My instantaneous power, or my peak power, as it's sometimes called, is a kilowatt. So sometimes it's important to remember that both of those are referred to as power. So it's important not to get confused. I remember when I was still pretty new at Ophir, we had a tender and there was a requirement for something about measuring so and so many megawatts. And whoa! And then digging into the details of the question, I realized they were talking about the instantaneous power during a pulse a couple joules, few nanoseconds long. Okay, we're talking about instantaneous power megawatts, even though the average power of the beam was just a handful of watts. So it's important not to get confused between the two. So let's just put all this together. And as I said already, I think at least twice, you'd be surprised at how often just this one slide can help a great deal in getting a good handle on what's going on. So again, we have energy per pulse that's measured in joules. We have average power, joules per second or watts. We also have peak power, instantaneous power, which is also joules per second, but instantaneous, not the same thing. We also have energy density, joules per square centimeter or per unit area incident on the surface that I'm interested in. And we're going to see how, where all of these are used. And of course, there's also power density in watts incident per unit area on my surface of interest. Just to give you an idea, power density or energy density might be the parameter of interest in applications involving diverging beams, such as those coming out of an LED or a fiber. Typical applications might use that kind of a beam for UV curing of adhesives or dental material or pigments or things like that, where what causes the adhesive to cure in that example is the total number of joules per unit area that it absorbs over the course of so many seconds. The power density incident on the surface, that's often called irradiance. I think I stepped on my microphone. Okay, hopefully not. Or the cumulative energy density deposited over some time window might be the critical parameter in that given process. So looking at some specific and pretty typical application examples, cutting, drilling in industrial settings. So cutting, drilling metal or whatever it is, welding, cladding. So what's gonna cause that the metal to vaporize and be cut or drilled is, I think it's pretty clear that we're talking about the power density, the number of watts, or more likely kilowatts per unit area that are being focused down onto that piece of metal. Enough kilowatts focused down into a small spot can cut, drill, weld, zap, etc. Also, though, the beam shape, the beam profile is going to be relevant because that affects the focusability, if there's such a word, the ability of the beam to be focused, and also the shape of the final spot inside of which my application, the work is supposed to happen. And that could make the difference between a good cut and a bad cut, a good hole or a bad hole, and so on. Here on the right side, you can see air cooling holes in a jet engine turbine blade that would have been, if not impossible, at least very difficult to produce using, traditional mechanical drilling. Welding, on the other hand, is typically done with pulsed beams, where each pulse consists of many tens, if not hundreds of joules, and usually one fires one pulse and then stops and checks, or checks once every X number of welds or whatever it is. So there, it's the energy density in each of those pulses that's really going to be making my welding process happen. Another example, military applications where we're using a laser to shoot down a target of some passing interest nowadays. We live in interesting times, as I said. So there, I might think that it should be no different than cutting or drilling. I'm focusing energy onto a small enough spot to be able to vaporize that material and drill a hole and damage the thing. Generally, though, it's not quite like that in these applications because the atmosphere, we're talking about long distances and fast moving targets. And the atmosphere is going to be causing a lot of scattering of the beams. So generally, the main parameter there is going to be the total power, and it's usually going to be a parallel beam. Usually, often, whatever. The power and power density needed for a given target type is going to depend on the material that the target's made of and the shape and orientation of its surface, as you can appreciate, and so on. Also, with a target that's moving fast, it's going to be more difficult to keep the beam on the same spot on that incoming missile for long enough to do the work. All of these things are the reason that this kind of application has been talked about for tens of years, but it's only in the last year or two that we're beginning to see systems becoming operational. There's a lot of research, by the way, being done using ultra short pulses, where a pulse might have only, let's say, a couple hundred millijoules, not a whole lot of energy, but the pulse is only a few picoseconds long. So the instantaneous power, the peak power, is a few hundred millijoules per picosecond. We're talking about extremely high instantaneous power, not average power, but instantaneous power. And there we can damage, vaporize, zap material through non-thermal mechanisms. There's all sorts of other ablation mechanisms that happen because of the extreme electric field. Um, you know, a really cool example I read about some time ago for ground-based targets. It's called laser-induced plasma channel. Basically, the air through which this ultra-short pulse moves gets ionized because of the extreme electric field. And so we have a conductive air channel. It stays conductive only for a short period of time. But during that short time, we then run an electric current through that ionized and therefore conductive channel of air, and that current zaps through the target and uses the target as its path to ground. It's kind of like using a laser pulse to enable Zeus-like throwing of lightning bolts at a target. That's pretty amazingly cool. Okay, here you just see an example. This is a Boeing test system, I believe, from about 15 years ago, using a 1 or 2 kilowatt beam to bring down a UAV in a system test. And this is from a long time ago in a galaxy far away. Couldn't help that. If you know exactly what I'm talking about, I can tell you more or less how old you are, and you probably know more or less how old I am. Actually, today I'm turning 63. I have no clue when on earth that happened. I blinked and here we are. It's fun though. I'm not complaining really at all. So now let's talk about the when, why, and how. Um, so let's consider a generic material processing application. Now, as we already said before, even regular light, classical light source light, can process materials. We mentioned that kid with a magnifying glass in the sunlight. an innocent insect who happens to be passing by. I've heard stories of other kids who are nerdy enough that they already know they're going to be physicists one day doing experiments like this. Other kids, of course. Nobody I know would ever have done anything like that. No, certainly not. Um, but for advanced applications, obviously, we want to have a process that we're in much more control of, and we're going to use a laser beam. So you have a generic material processing application. You've got a laser beam, suitable wavelength, suitable power, et cetera, for the application that I'm going to use it for. Some kind of a focusing lens, and then the beam gets focused down. If it doesn't meet anything on the way, it'll continue past focus and it'll defocus. But I'm not going to let it do that. I want to use that beam, so I have a target surface that I want to cut, weld, drill, and so on. And here you see the space inside of which the power density is high enough to have the required effect on the material. Okay, very oversimplified, but not inaccurate material processing application setup. But what happens if something changes in the laser, or maybe the delivery optics change their optical characteristics a little bit because of heating effects or anything like that, or something, one of the optical components moved out of alignment, the space inside of which the power density is high enough to make the work happen might shift. And we could suddenly and unexpectedly find ourselves with the target material outside that space. And the resulting part, right, could be different than what the process is designed to produce. A patient might just have been harmed if it's a medical application, or increased scrap might have just pushed a production line from profit to loss. So obviously, we need to measure the relevant parameter or parameters accurately so that we can control what our process is doing, so that we can keep it stable and predictable. So here you see just a few examples: an industrial laser cutting application. On the right side, that's a dental laser, everybody's favorite, right? On the bottom, we see via holes drilled in a silicon wafer. And again, we can appreciate that even a tiny mistake there can cost somebody a lot of money. Just a few more interesting examples: laser fusion. I can't not mention that without getting into the physics as much as I would love to. But in order to fuse hydrogen atoms into helium and get all that gargantuan amount of energy out, I have to overcome the electrostatic repulsion among the hydrogen nuclei, protons, right, plus, plus, they repel each other. So one of the ways that's being very intensively worked on nowadays, and has been for a long time, is inertial confinement fusion, where basically we take a frozen pellet of hydrogen, not exactly hydrogen, two isotopes of hydrogen, okay, and we 2-3 millimeters wide, and we zap it simultaneously from all directions with a whole bunch of laser pulses, and we do that so intensively and so uniformly that the whole exterior of that frozen sphere of hydrogen gets zapped and explodes, and the inner core gets extremely compressed, sufficiently extremely compressed to overcome that electrostatic repulsion and achieve fusion. I've horrifically oversimplified this, but you get the idea. If those pulses aren't exactly uniform, if one side of that pellet explodes a tiny fraction of an instant before the other side, then it's not going to be compressed and we're not going to achieve fusion. A little bit more down to earth on the lower image is a laser marking of a serial number on a jet engine blade. One of our customers showed me this. They explained that there is an industry requirement, not a regulatory, but an industry requirement, that all turbine blades be marked with the serial number in case, God forbid, some accident is traced to a faulty blade. And they want to locate every jet engine on the planet that has in it a blade that was produced on that same machine on the same day during the same shift, so that they can do preemptive maintenance. So they had, interestingly, the laser marking system used a laser that was something like 18 or 20 watts. It's not a lot of power, but when it's focused down to a small enough spot, it can burn a serial number onto the metal of the blade. So we talked about the need for accurate measurement. So far we talked about the measurement. Now let's talk about the accurate. So what do we mean by accuracy? It's an easy word to use when you say it fast, but what does it mean? It's essentially a measure of how close the reading that's being that I'm getting from this instrument, the measurement of power, let's say, how close that reading is to the absolute truth. If my instrument tells me that the power in this beam is 1.0 watts, how close is that to the real power? Now, I don't know about you, but I don't have too much access to absolute truth. So obviously, what we all mean in the industry is how close is it to what we're all get some kind of a reference standard that we're all going to agree on. So if a manufacturer of a laser power meter, such as Ophir, says that this power meter is accurate to within plus minus 3% of NIST or of PTB. So as long as we know what we're talking about, then we know that, okay, it means that the reading is accurate to within so many percent of what NIST, let's say, would say the power of this beam really is. This is a huge oversimplification, but you get the idea. Calibration is the process of comparing the instrument that I want to offer you to a reference, let's say a NIST traceable laser power meter, a meter that was calibrated by NIST themselves, or that was calibrated against another one that was calibrated by NIST. Okay, there, we won't get into all of that. And I'm comparing the unit under test to that reference to know exactly how accurate the instrument is. So I can then tell you, okay, here's a laser power meter and I calibrated it so I can tell you that it is within plus or minus X percent of a NIST traceable reference, and you can use that information. Often, although not necessarily, we can then adjust the instrument so that it measures as close as possible to that NIST reference, but I don't have to do that strictly speaking, because even if I take my unit under test and I compare it to a NIST reference, and I now know that it's exactly 16.5% low compared to NIST. Even if I leave it like that, but if I tell you this is precisely 16.5% low compared to NIST, you can work with that because you know exactly how accurate it is. Usually, manufacturers of measurement instruments will also include the adjustment as part of the calibration. If any of you are QA professionals, then you're probably the only people here who appreciate why I got as pedantic as I just did. But it is important to, when we're dealing with quality, we want to be as pedantic as we can. Users, let's say integrators of laser systems, often refer to the calibration not of their measuring instrument but of their laser system. What they mean is they're using a laser power meter, let's say, or a laser measurement instrument that they get from a manufacturer such as Ophir to make sure that their laser, when their system thinks that it's driving their laser to produce 100 watts, that it really is producing 100 watts. So strictly speaking, I don't know if that would be called calibration by a QA professional, but we all understand what we mean, so we're good. So here you see just an example. This is something that we've seen in quite a few laser-based surgical systems, where what they'll often do is have a small detector inside the system looking at a tiny percentage of the power coming out of the laser, maybe a beam splitter, or in gas type lasers, there's still the rear leak, whatever it is. And they're monitoring the laser full time that way, but there are limitations to that. There's drift there. It doesn't pick up changes that happen farther downstream in the optical chain, whatever. But then what they do is they have an opening in one of the side panels of the machine, and there's a larger full-blown laser power, let's say, meter that measures the full power of the beam. And let's say it's a surgical system, the user, the doctor, will once a day, once a week, before each procedure, whatever the needs are, take the handpiece, stick it into that hole, fire the laser once, and the system will compare what it's really measuring to what that monitoring detector thinks the power is, and if it needs to make any internal adjustments, it does so. It's a very neat solution that we've come across quite often. Okay, typical laser measurement instrument consists of two parts, a sensor and a meter. In the old days at Ophir, we used to call them a head and a display, but now we call them a sensor and a meter because it's a bit more of an accurate description of what each one does. The sensor is the laser facing end, the input end. It's the transducer that receives the laser beam to be measured and produces some sort of signal that represents the parameter of interest, such as power, if it's a power sensor. In Ophir sensors, for example, the raw output signal is an analog current. the calibration data, which will tell the rest of the measurement instrument how to interpret that current and turn it into a reading of power. It will know the constant of proportion between the current and the power, which will depend on the wavelength and on all sorts of other things, is stored in an EEPROM inside. Oh, that's a sensor. It's stored in an EEPROM in that connector at the end of the cable coming out of the sensor, and the meter is going to read that. The meter, some manufacturers call it a display, as I said, console, controller. Every manufacturer uses their own terminology. Now that's the user-facing end, which measures that analog signal coming out of the sensor. So Ophir meters are, in essence, very sophisticated current meters. And it reads the calibration data in that EEPROM, processes the signal, which may include all sorts of calculations and whatever, and then outputs the measured reading, possibly via a numeric display for a human user, as in the example we see here, but there may be other ways, maybe through a digital interface to a PC with software running. The software might be provided by the instrument manufacturer, or maybe it's the user's own software, whatever. Or if it's an OEM instrument integrated inside a user's host system, such as one of those surgical systems, it might be communicating with the host controller that runs the overall system, whatever the case may be. In our discussion, we're going to be looking mainly at the sensors, since the differences among them are physical. The wrong choice of sensor could mean incorrect measurement, no measurement, or maybe a damaged sensor. We'll talk about that in a second. The choice of meter, on the other hand, is functional. It's all about how you want the results to be shown to you graphically. Maybe you'll want some mathematical operations performed on them, the ratio between two sensors or whatever. So we'll look at various types of sensors briefly. We will come back to the meters, don't worry. Note, by the way, that the meter and the sensor might, in some cases, be combined in a single device, an all-in-one device that has advantages and disadvantages. We're going to look at some of those devices shortly and say a few words about when they might be the preferred approach. So for measuring low power, nanowatts, all the way up to maybe a couple hundred milliwatts typically, we're generally going to use photodiode-based sensors because they have the sensitivity. Here on the left half of the screen, you see some Ophir photodiode sensors. We have sensors that can measure from picowatts actually up to a couple hundred milliwatts, various types for different spectral regions, silicon, InGaAs, germanium. For powers from milliwatts, let's say up to 100 or hundreds of kilowatts, we're generally going to use thermal sensors. Not going to get into the physics of how they work, much as I would love to. But we're going to use, it's a sensor that absorbs the heat that absorbs the laser beam. The resulting heat gets measured and is an indicator of the power that was in the beam. I said milliwatts. At Ophir, we have some thermal sensors that can measure as low as a few microwatts, which is very sensitive for a thermal sensor. But usually for that kind of power, all of the things being equal, we might choose a photodiode-based sensor instead. For measuring extremely low powers, some cases, we'll use something called a radiometer. The idea here is that the lower limit of what a sensor can measure is ultimately dependent on its internal noise. And that noise is more or less white, meaning it's spread across a very wide spectrum. What we do here is we modulate the signal, which is the beam that we're trying to measure, so that it sits on a single frequency. We do this by optically chopping the beam at a very precise frequency. So on the component on the left is an optical chopper set to a very precise frequency. And then we use a digitally synthesized lock-in amplifier to pass only signals that are riding on that frequency. The noise and background light is broad spectrum, so almost all of that gets chopped out. So this trick lets us use a suitably broadband sensor to measure signals that are way below what would normally have been the noise floor of that sensor. In some models, we actually can go down to as low as the femtowatt range. You heard that correctly. When we're talking about diverging beams, we mentioned that briefly before. Such as beams coming out of LEDs or many types of laser diodes or fiber tips. So there are some challenges. The beam is widely diverging. So unless I bring my sensor very close, most of the beam is going to miss my sensor. Sometimes I can come close, but sometimes for all sorts of reasons, I can't. So if I need to capture the entire widely diverging beam, usually what we use is something called an integrating sphere, which is a hollow sphere, all different sizes, the inside of which is white and very diffuse and very reflective. So the beam comes in and then gets mishmashed and uniformly spread around the inside of the sphere. And then with or without a built-in sensor, in this case, you can see that there is a sensor there. The sensor sees a sample of the beam, but because the beam's been uniformly mishmashed around, that sample is a good representation of the total power that's going on inside the sphere, and we can do a measurement that way. If the sphere is not too small, we can have some additional ports, which allows us to sample the light out to additional measurement instruments. I might want to measure the wavelength, a spectrometer, or a fast photodetector to measure the temporal pulse shape, and so on. In many other applications with widely diverging beams, I might not care about the total power in the beam. We mentioned earlier, I might have a widely diverging beam for UV antibacterial applications in the food industry. So there, I don't care, I have a bank of UV fluorescent lamps illuminating a work surface where my samples, my food, whatever, is moving along. And I don't care about the total power coming out of the bulb. I care about the power density or the cumulative energy density per unit area of my target material. So I'm interested in the power density or the energy density. We often call those the irradiance and the dosage. So at Ophir, we actually have a few sensors that are specifically meant for that. Here are two of them. One of the challenges in this kind of measurement is that the light is coming from all sorts of different angles, and most detector types have some degree of angle dependence. So here you can see on the one of the things you might be able to notice is that there's a diffuser built on the aperture of that detector, so that the light coming in gets diffused, gets mishmashed around, and it gives the sensor a proper cosine response to get rid of the dependence on the angle. The one on the right is the same idea, but it's meant for shorter wavelength UV. So the body is made of anodized aluminum, and the cable is also a special cable so that it can survive the experience of all of that UV exposure. Let's talk a little bit about limitations. The spectral behavior, the spectral response of my sensor is going to depend on that first surface that receives the beam. Different materials absorb different wavelengths to different degrees. Here you see spectral response curves of a bunch of different absorber types that we use at Ophir. The absorber is also going to determine the damage threshold, how much power density, and in the case of pulse beams, energy density, the sensor can withstand without getting damaged. Here you see some pretty cool examples of damage. The one on the right, you can see that the user was using this sensor to measure the beam in a laser marking application, and they were apparently not aware that you don't have to measure at the focal spot. So they laser marked the sensor. The cost of replacing a damaged disk is somewhere between a third and a half of the cost of a new sensor. So this is an important sentence to keep in mind. You don't have to and you don't want to measure at the focal spot. It's the same number of watts and joules, defocused as focused. Very important. Additional limitations, the maximum power that a sensor can handle. Power is coming in, it's getting turned into heat. We want that heat to get out at least as fast as it's coming in, or the sensor is going to heat up and eventually something's going to fail. There are tricks to get around that. Many sensors are designed to be able to handle up to such and such a power constantly, because the body design can dissipate heat only up to that rate. But for short-term intermittent measurements, it can maybe go higher. Okay, so sensor body design is what's going to determine the maximum power rating. The sensor in the middle, you can see that its body is designed as a sort of a heat sink. In some cases, there will be a fan there to give it an additional heat dissipation capacity. For higher power, kilowatt, and upward, industrial applications usually will use water-cooled sensors, such as the one you see on the right. In general, in those applications, the lasers themselves are also water cooled, so there is usually going to be cooling water infrastructure at the facility. Um, Maximum beam size obviously is limited by the aperture of the sensor. Keep in mind, though, that it's not always quite as simple as that. For a Gaussian beam, for example, there's quite a bit of beam outside what appears to our eyes as the beam's outer limits. We don't want to unknowingly cut off outer wings of the beam and get incorrectly low measurements and not even know about it. That's an effect that we call vignetting, unknowingly cutting off the outer bits of a beam because we thought that the beam was this big, but there's, you know, as a former colleague of mine once said, the outer limits of a beam, it's kind of like talking about the outer limits of a cotton ball. It's not a clearly drawn line. In many applications, such as welding, as we mentioned earlier, we want to measure the energy of one pulse. Uh, that pulse may have an energy of many hundreds, if not thousands of joules. We'll usually use a thermal sensor for that. What happens with a thermal sensor is that the heat that is generated by absorbing the laser beam moves through the body of the sensor on its way out to freedom, and that heat flow gets measured. So the output signal, remember we said that in the case of Ophir sensors, at least, it's an analog current. So as the beam starts to come in, the heat starts to move, the output signal will begin to rise. And if it's a pulse, it'll maximize, and then after the end of the pulse, the last bits of heat make their way out, the signal comes back down again. The meter keeps track of this and calculates the area under that curve, the integral. Don't worry, you don't have to do that. Last time I calculated integral, I don't want to think of how many decades ago that was. But the area under that curve is the total energy that was in that pulse. So generally speaking, thermal sensors have a time constant on the order of seconds because the heat has to propagate through a disk. Um, so after we fire that pulse, usually what will happen is that the output of the meter will tell you, wait, don't fire another pulse yet. And then when it's finished and the meter senses that the last of the heat has gone and it does its processing, displays the result, and then it tells you that it's ready for you to now fire another pulse. For repetitively pulsed beams, then you can already appreciate that we won't use thermal sensors. We'll use other sensors, usually pyroelectric sensors. They can respond to every pulse at up to various repetition rates, depending on all sorts of details, from a few tens of hertz, hundreds of hertz, 20 plus kilohertz, or whatever the case may be. In some cases, for very low energies, the energy sensor won't really be pyroelectric. It'll be based on a photodiode, actually, and some of those can measure down to picojoules. The configuration is the same, so it's invisible to the user in the meter, but whatever. And here you see a meter displaying the energy. This meter also displays the measured pulse repetition rate. So if you see that the energy that you're getting doesn't make sense, it's not what you were expecting, and you notice that the displayed pulse repetition frequency is very, very jumpy, that's probably a good indicator that what you're measuring is noise and not actual pulses. Okay, similar limits, maximum energy based on the design of the detector, minimum energy is the noise. These are all listed in the data sheet of any sensor. Spectral range, again, it's a function of the absorber that's used in that particular sensor. That absorber will also determine the maximum energy density. That's another type of damage threshold. Every sensor has its own characteristic maximum pulse repetition rate up to which it can keep up with the pulses, and the maximum pulse duration. So there's a lot of factors that go into selecting the right sensor. Don't panic. We have on our website, and I believe other. I need. I'll quickly. Sorry. Other manufacturers probably have similar stuff. We call it our sensor finder. It's a software tool on our website. I'll show you in a second where to find it. It asks you for the parameters that it must get from you in order to give you an unequivocal choice of sensor. So it asks you for whether it's CW or pulse, the wavelength, the beam diameter, et cetera, et cetera. And then it'll give you a list of sensors that can do the job, usually in increasing order of price. So the first few that come up are the ones that you're going to want to take a closer look at. That's an interesting thing. We also have a meter finder. Now, as I said, the choice of meter is a question of what kind of functionality you want. It's not physical. So this is not a software tool. It's really a comparison table. What type of measurements, what functions are available in each of the different meter models and so on. I'd like to draw your attention to a short video we have at this link here, how to choose the right meter display video. That's a link to a video that we have. It's also on YouTube on our social media channels, and that's like a 4-minute long video that gives you a basic idea of how to start the thought process of selecting the meter that's most suitable for what you need to do. Where to find these? So if you start at the main Ophir Photonics page, so here you have products on top. If you click on products down here, you see links to the laser sensor finder and the power meter finder. A different way to get to those, same main page of Ophir Photonics, but in this time you just scroll down to about halfway down, 2/3 of the way down, you'll see these big banners that are links also to the sensor finder and meter finder. So just as an example, one of the first questions you're going to want to ask yourself when you're considering what meter is best for your needs, one of the first questions will be, do you want a handheld or desktop meter with a display? Most of those can connect to a PC also, USB, Ethernet, whatever. Or will all of your work be with a PC? And so maybe you can use one of these virtual meters, the two that you see at the bottom, which do everything the meter does except for the displaying. That they outsource to the software, because it's software, it has a lot more capabilities in terms of graphics and whatever it is. So that's just an example. Let's just a few words about beam profile briefly, and then we'll conclude. And best way to illustrate the relevance of this is by a case study. This is actually on our website from some years back. A customer that manufactures various medical devices. What we're looking at here is some sort of implantable medical device. I have no clue what this thing does, but its manufacturing process involves a very critical welding step. Now, this customer was producing this component in parallel at two different facilities. Both of these facilities had the same manufacturing process, the same laser system, the same everything, but the welds coming out of one facility were always good, and the welds coming out of the other facility were very often failing, luckily at QC inspection and not, God forbid, later on already in a patient. I couldn't figure out what the problem was because the processes looked the same. So they asked us to help them look into this, and it turned out that yes, the lasers were the same, the systems were the same, process was the same, but in one of those two facilities, something in the optical chain had gone out of alignment. The two beam profiles were not the same, and so the shape of the beam was not what it was supposed to be, and so the weld was not what it was supposed to be. We mentioned earlier that the focusability of the beam and the resulting shape of the focal spot, and that's the weld, can be affected by the beam profile. We measure beam profile, two main methods. One is a camera, such as the one you see here, CMOS CCD, usually camera that looks into the beam. Very often it'll need some kind of attenuating optics, lots and lots and lots of details. And then most of the power is in the software, lots of very sophisticated calculations and processing go on here. Here you see a typical screenshot of our beam profiling software. Lots and lots of information. Our application engineers put a lot of time into helping the customers understand exactly what their laser is doing, not just its power, but what the beam looks like. Because a lot of times that's easy to miss. A second method is using, it's known as a rotating slit type of a beam profiler. Here's what one of those looks like. Again, I'd love to get into the physics of that, but we're not going to mention. Way beyond the scope of our conversation today. Also, all sorts of specialty items, instruments for measuring M², focal spot analyzer. If you don't know what on earth I just said, apparently that means you don't need one of those, but whatever. A very cool solution that was introduced a couple of years ago by Ophir Spiricon is based on a physical property of light known as Rayleigh scattering, where the high concentrated light around the laser beam's waist, if the beam is high enough in power, is scattered off air molecules in its vicinity and captured by a camera. And then analyzed. This allows for an analysis of the laser beam's waist without coming into contact with the beam. So the result is a beam analyzer with no cooling required, no moving parts, and essentially no upper limit on the power of the beam that it can analyze. And since it's a camera-based system, it provides data at video rates, so you can keep track not only of the shape and the focal spot location, but the focal spot stability and the movement as the laser warms up, and things like that. So you're also getting time-based characteristics, the location of the spot over time, as well as other parameters like beam divergence, M², beam parameter product, BPP, all of which can be provided dynamically in real time. I said we'd have a look at some all-in-one instruments. Here are a few examples of multifunctional instruments. 3 out of the 4 are self-contained all-in-one devices. These two are mainly optimized for use in additive manufacturing process chambers. They can sit inside the chamber, close the door, they communicate Bluetooth or other options with an instrument outside. If it's Bluetooth, then with your Android device, for example, or iOS or whatever. The top one is actually a combination beam profiler and power meter. The bottom one is a power meter. This one here is a high power meter meant for factory floor integration. Think of an automotive production floor where you don't have a human user holding in a meter pressing buttons. You've got a central server controlling a whole factory floor. That's what this instrument is designed for. And this one is it's not self-contained. It needs a meter, but it is multifunction. It's a integrating sphere with two built-in detectors, one for measuring power, one for measuring the temporal beam shape. And there's also an additional output for sampling light out to a, let's say, spectrometer or some other kind of additional instrument. Okay, so in summary, okay, we're just slightly past what I estimated, but hopefully still within our limits. So we talked about the importance of measuring our laser's performance by keeping track of the appropriate parameters that are relevant to our application. We discussed a little bit about the meaning and importance of accuracy and what calibration involves. We looked at some examples of instruments for measuring a laser beam's power, energy, beam profile, temporal pulse shape, and a few others. Our website has also lots of videos and articles, including recorded on-demand webinars about how to choose a sensor, how to choose a meter, basic technical principles of the different types of instruments, and so on. You're warmly welcome and encouraged to make use of those. And most important of all, speak to us if there's any way at all in which we can help you with your application.